Welcome to qnawire.
So here we have a rod from x equals to 0 to x equals to a. So let's draw the axis first. So let's say this is our x-axis and this is, excuse me, our y-axis. And this is the negative x and negative y. And we have a rod from x equals to 0 to x equals to a. And the charge in the rod is uniformly distributed over the whole length of the rod, and the information that we are given is oops, the length, which is a, and the charge on the rod, which is denoted by capital Q. Now in the first part we have to find the x and y components of the electric field. So basically we have to find the electric field of this rod. So let's do that. Now at any point on the x-axis, the vertical component of the electric field is 0. And one more thing, we have to find the x and y components of the electric field produced by the charge distribution at points on the positive x-axis where x is greater than a. So we have to find the electric field at any point outside this distance. So let's say at this point here. So let's call this point to be P. And let's assume that P is placed at a distance x from the origin, and we have to find the electric field at this point P. Now again, as I said, at any point on the x-axis, the vertical component of this electric field exerted by this charge distribution is 0. Now let's find the linear charge distribution lambda of this rod. So lambda will be equal to dq over dl. So lambda is actually charge over, since charge is uniformly distributed, so we can directly divide the total charge over the total length. So this gives lambda to be q over a. Now since charge is uniformly distributed throughout the rod, we can't just take directly the middle point or the whole point and find the electric field. We have to cut the rod into small sections of small charges and find the electric field of that particular small charge at this point P. So let's say we take this section and let's say that this section is dl. So this means this is at a distance L from the origin, which means that the rest of the distance, this distance is A minus L. So the distance of dl from P is equal to x minus L yeah. So this is the distance of dl from P. Now the horizontal component, horizontal differential component, that is the horizontal component of electric field due to this segment or this the small charge residing in this small segment of the rod will be equal to, so let's call that dex. So that will be equal to k times, so the charge in this small segment will be lambda times dl, because lambda is the uh, linear charge distribution. So lambda times the length will give us the charge of that section, over square of the distance of that segment from the point where we are calculating the electric field. So that is x minus L whole square. And obviously dEy is equal to 0, which means that the vertical component will be equal to 0, because we are uh, everything is uniformly distributed on the x-axis, and also the point that we are considering to find the electric field is also on the x-axis. Therefore there can't be any component of electric field on the y-axis. So the total electric field is actually electric field that is residing on the x-axis, the electric field on the x-axis. So E will be equal to integration of E will be equal to Ex, and that will be given by integration of dEx, where dEx is the electric field of a small section on the rod. And since that small section is with respect to the length of the rod, so let's substitute that. So we are changing dl, and accordingly our electric field will change. So in order to find the total electric field, we must integrate over the total length. And since our length varies from 0 to a, this value L varies from 0 to a. So our limits are 0 and a. So let me go to the next page. So E is equal to integration of 0 to a k lambda dl over x minus L whole square. Now here k and lambda are constants, so we can take it out of the integral. And integration of this is negative 1 over x minus L. And the limits are 0 and a. And substituting the limits in place of x, we get 1 over a minus L minus of 1 over 0 minus L. So these are the limits. And this gives the electric field to be k times lambda 1 over, oops, I did a, so instead of substituting our values in place of x, we need to substitute them in place of L, because we are integrating over dl. So let me just correct that part. So we have negative 1 over x minus L, 0 to a, and we have to substitute these limits in place of L, because L varies from 0 to a, and those are the limits we integrated over dl. So our limits should be placed in place of L. So we have negative 1 over x minus a, the upper limit, minus negative 1 over x minus 0, the lower limit. And this gives k times lambda 1 over x minus a minus 1 over x. Let me just cross check. Oops, I missed a place. So and there is a negative sign over here which I forgot. So yeah, so this is how the integration should look like. And after putting the limits, you should arrive something that looks like this. and substituting the value of lambda, you get the electric field to be K times Q over A 1 minus 1 over x minus A minus 1 over x. So that's the electric field. And since, as we discussed, the electric field comes entirely by integrating over the horizontal component of electric field, and there is no electric field in the y direction. And also, since the charge on the rod is positive, which means that the electric field at a point P will be away from that charge because Q is positive. This means that dEx has actually a direction on the towards the positive x-axis, and therefore the total electric field will also should also point in the positive x-axis. So the direction is I cap. Now in the second part, we have to find the force exerted on a charge small q. So since small q is also positive, therefore the force is going to be repulsive, and this q is placed at a distance r from the rod. So q is at a distance r plus a from the origin. So the force will be equal to q times the electric field at this point, which is r plus a from the origin. And since we already have an expression for electric field at a distance x from the origin, so we can substitute x as r plus a and find the electric field at that point, and then multiplying that with q will give us the force. So we will use this expression. So we have kq over a, and our x is r plus a. Oops. And then again we have another x over here, and let's mark the vector signs, and this has a direction I cap. So this is equal to k q small q times capital Q over a 1 over r minus 1 over r plus a. And again, since this q charge is positive, therefore the electric force should point along the direction of electric field and will be repulsive because both the charges are of the same sign. So here we have the expression, the vectorial expression of the force. So in the third part, we have to find the force when the charge q is placed at a large distance from the rod, which means that r will be very, very greater than a. So we already have the expression of this force. So in order to do that, let's solve this magnitude of the force first. So we have our a 1 over r minus 1 over a. So solving this part inside the parenthesis, we'll get a value that's equal to kq q over r square r plus a minus r over r times r plus a. And this is equal to kqq times r over r times r plus a. Now here is the time to put this condition r very, very greater than a. So this means that since r is very, very larger than a, therefore r plus a will be nearly equal to r. So we can put this limit over here. So Let me solve this, or I can solve that part over here only. So this is what we got for force. So F will be equal to KQ times R over R times. So we put this limit over here. So that will nearly be equal to R, and this gives the force to be equal to KQQ over R. And oops, I forgot there was an A here. So A here, and this is actually A. I did a calculation mistake. I'm sorry about that. A, so here we have A, here also we have A, and these two cancel out, and we get the force to be KQQ over R square. So if you compare this to a Coulomb force, this actually means that when the charge small q is situated at a very large distance from the rod that has a charge capital Q, then the rod acts as a point charge, and therefore you can treat it like a point charge, and force on a charge due to a point charge is something like this: k times q times capital Q over the distance between the two charges, and that will be nearly equal to R because q is now a point charge, so square of that distance. Thank you.